Today we're going to solve an example problem of Chapter 8 Reacting Systems, Combustion Process. Combustion is also known as burning, in which it is the basic chemical process of releasing energy from a fuel and air mixture. Let's proceed to our example problem. A certain natural gas has the following volumetric analysis: 65% of methane, 8% of hydrogen, 18% of nitrogen, 3% of oxygen, and 6% of carbon dioxide. This gas is now burned completely with a stoichiometric amount of dry air. What is the air-fuel ratio for this combustion process? We have the given values. Methane is 65%, which is equal to 0.65, hydrogen in 8% equal to 0.08, nitrogen is 18%, which is equal to 0.18, oxygen is 3%, which is 0.03, and carbon dioxide is 6%, which is 0.06. We need to find the air-fuel ratio for this combustion process. Considering 1 kilomole of fuel, the combustion equation can be written as 0.65 kilomole of methane plus 0.08 kilomole of hydrogen plus 0.18 kilomole of nitrogen plus 0.03 kilomole oxygen plus 0.06 kilomole of carbon dioxide plus the theoretical amount of air of oxygen plus 3.76 kilomole of nitrogen, which is balanced to the coefficient X of the carbon dioxide plus the coefficient Y of the dihydride oxide plus the coefficient Z of the nitrogen. The unknown coefficients in the above equation are determined from mass balance. Carbon 0.65 kilomole plus 0.06, which is from the reactant, would be equal to X, which is from the product. So we solve for X, we will have 0.71. In hydrogen, we have 0.65 times 4 plus 0.08 times 2, which will be equal to 2y. We solve for y, we will have 1.38. In oxygen, we have 0.03 plus 0.06 kilomole plus the theoretical amount of air, which will be equal to X plus y over 2. So we have to find the theoretical amount of air. We will have 1.31. In nitrogen, we have 0.18 plus 3.76 multiplied the theoretical amount of air, which is equal to Z, which will be, we'll solve for Z, and the value of Z would be 5.106. We substitute the value of the coefficients into the combustion equation to have 0.65 kilomole of methane plus 0.08 kilomole of hydrogen plus 0.18 kilomole of nitrogen plus 0.03 kilomole of oxygen plus 0.06 kilomole of carbon dioxide plus 1.31 kilomole multiplied to oxygen plus 3.76 kilomole of nitrogen, which is balanced to 0.71 kilomole of carbon dioxide plus 1.38 kilomole of water plus 0.06 kilomole of nitrogen. So the combustion is now balanced. We need to proceed in solving the air-fuel ratio. But we have to note that the molar mass of each element, it can be found in table A-1 in our property table. The air-fuel ratio for this reaction is determined by taking the ratio of the mass of the air over the mass of the fuel. From our combustion equation, mass of air is equal to 1.31 kilomole. This value is the theoretical amount of air, which will be multiplied by 4.76 kilomole. 4.76 kilomole is the number of moles in the air. We have 1 kilomole of oxygen will be added to 3.76 kilomole of nitrogen. Thus, we have 4.76. Then, after knowing the value of the moles in the air, we have to multiply the molar mass of air, which is 29 kilograms per kilomole. We then cancel the unit kilomole to have unit kilogram. Our mass of air is 108.8 kilogram. Mass of fuel is equal to 0.65 kilomole times 16 kilogram per kilomole plus 0.08 kilomole times 2 kilogram per kilomole plus 0.18 kilomole times 29 kilogram per kilomole plus 0.03 kilomole times 32 kilogram per kilomole plus 0.06 kilomole times 44 kilogram per kilomole. We have to cancel the unit kilomole. The mass of fuel is 19.2 kilogram. Now that we have the value of the mass of air and mass of fuel, we can now solve for the air-fuel ratio. We have the formula air-fuel ratio is equal to mass of air over mass of fuel. Substituting the values, we will have 180.8 kg over 19.2 kg. Then, our air-fuel ratio would be equal to 9.82 kg of air per kilogram of fuel. That's the end. See you in my next video.